Welcome to Talk Tensors. If you ask a modern AI to write a complex, multi-threaded script, it can often do it in seconds.
Yeah, it really looks like magic.
It does. It looks like absolute magic. But if you ask that exact same AI to check its own work, to write the unit tests for the very code it just generated.
That's where it all falls apart.
Exactly. It suddenly develops this catastrophic blind spot. It will confidently pat itself on the back, generate a suite of highly biased tests that neatly avoid its own logical errors, and just pass critical, sometimes disastrous bugs straight into your production environment.
Which is terrifying if you're deploying these things at scale.
Right. So you are listening to a deep dive today that serves as a massive shortcut for you. If you are trying to understand the absolute cutting edge of agentic AI, specifically the breakthroughs in multi-agent code generation, this is the architecture you need to know.
Yeah, we're unpacking a highly specialized, streamlined three-agent framework today.
And it intentionally, forcefully isolates code generation from test generation.
The central premise we're looking at revolves around a framework known as AgentCoder.
AgentCoder, got it.
Right. And the single most important contribution here isn't adding more complexity, which, well, that's kind of been the trend lately in AI research.
Oh, definitely. Everyone just wants to throw more agents at the problem.
Exactly. But AgentCoder introduces a rigid separation of concerns. The architecture completely divorces the programmer entity from the test designer entity.
So they can't talk to each other at all.
Not at all. And then it grounds both of those isolated language models using a third non-LLM component, which is a test executor.
Okay, a test executor. So we have a triad.
Right, a triad. By forcing this strict separation, by preventing the model that writes the code from having any influence over the model that tests it, this framework just shatters previous benchmarking records.
Wow.
Yeah. And it does so while drastically cutting down the token overhead compared to the bloated, chatty multi-agent swarms that we've seen dominate in the space over the last year.
Which is the perfect place to start, I think. Because to really appreciate why a strict three-agent triad is so revolutionary, we kind of have to look at the mess of bloated agent committees that the industry just went through.
It really was a mess.
It was. So let's trace the lineage a bit. How did language models learn to code in the first place, and what was the state of the art right before this triad architecture was introduced?
So tracing that lineage is crucial because it explains the specific cognitive bottlenecks these models hit.
Right.
If we go back a few generations to the early pre-trained model systems like CodeBERT, BART, or CodeGPT.
The classics.
Exactly. We're looking at foundational architecture trained explicitly on massive code corpora. They were basically just scraping millions of public GitHub repositories.
Okay, so they're ingesting all this syntax.
Yeah, and what these models achieved was laying the syntactic groundwork. They learned the grammar of Python, the boilerplate of Java, the memory management structures of C++ ACK.
Right, so they learned how to type the language without making syntax errors. They got the semicolons and the indentation right, but they weren't necessarily solving complex, novel logic puzzles yet.
Exactly. They were phenomenal at autocomplete, but they were limited in structural reasoning. Even when advanced iterations like Graph CodeBERT started integrating graph-based representation.
So they weren't just reading left to right anymore.
Right. They were beginning to map data flow, getting a sort of abstract understanding of how variables interacted, but still limited. Then we transitioned into the era of massive scale foundation models.
The multi-billion parameter engines we use today, like GPT-4.
Exactly. These models had seen so much data, and their context windows had expanded so dramatically that they could generate highly functional, complex code snippets zero shot.
Just right out of the gate, first try.
Right. But the realization hit almost immediately. Asking the model once in a single pass yields really brittle results.
It might look right, but it fails under edge case pressure.
Precisely. So the industry pivoted to prompt engineering tricks. We saw the rise of techniques like self-refinement.
Where you prompt the model to review its own output and optimize it.
Yeah, or self-debugging, where you take the inevitable error messages and feed them right back into the same context window, asking the model to patch its own mistakes.
But those prompt engineering tricks all hit the exact same wall, right? It was just what we would call a single agent bottleneck.
Right. You're using one monolithic session.
The classic example is CodeCode, using a chain of thought prompt to make one single LLM session do all the heavy lifting.
Yes, you tell it, write the code, and then in the very same breath, using the very same attention mechanism, write the test cases to prove to me that your code works.
And that single agent approach possesses a fundamental, unavoidable flaw rooted in the architecture of transformer models. It's split focus and context window anchoring.
That's the core issue. When an LLM is optimizing its neural pathways, when the tension heads are firing to generate a specific algorithmic approach for a code snippet, it becomes anchored to that logic.
It gets tunnel vision.
Exactly. So when it subsequently attempts to generate rigorous objective test cases, its effectiveness drops precipitously. The model is using the same context window.
It's looking back at the code it just wrote.
Yeah, and it inherently assumes its own logic is correct. It completely lacks the adversarial distance required to look for edge cases that would break the specific implementation it just committed to.
It's the classic grading your own homework problem, but on a mathematical level.
Perfect analogy.
So the industry recognized this single agent bottleneck, and the natural, almost reflexive reaction of the tech world was, well, if one AI isn't smart enough to do it all, let's throw a whole committee of AIs at the problem.
Which ushered in the multi-agent era.
Right. We saw frameworks that tried to simulate an entire corporate software development lifecycle inside the machine.
We saw systems utilizing 5 distinct agents, simulating product managers, system architects, project managers, software engineers, and QA engineers.
Some even went up to 7, right? Like chat dev.
Yes. Chat dev pushed that number up to 7. They built these virtual software companies inside the context window, with agents passing natural language messages back and forth to simulate a waterfall or agile development process.
Which, I mean, it sounds incredibly futuristic on paper. You have a little virtual startup living in your GPU.
It sounds great until you measure the performance.
Right, because when you look at the actual output, you start running into massive crippling issues. 2 specific problems jump out when analyzing those bloated multi-agent systems.
The first one is the feedback mechanisms. They were incredibly weak.
Yeah, you look at a 5-agent system with a dedicated simulated QA agent like MetaGPT, and its test accuracy on a standard dataset like HumanEval was hovering around 79 to 80%.
It's literally missing a fifth of the bugs.
Exactly. And the second issue is the token overhead. It's absolutely astronomical.
The token consumption becomes prohibitive almost immediately. Think about the mechanics of those multi-agent frameworks.
Agent A talks to Agent B.
Right, Agent A, the architect, sends a design document to Agent B, the engineer. But Agent B doesn't just read the code. It has to process the entire conversational history to maintain its persona.
Oh man, the pleasantries.
Yes, it generates pleasantries, it establishes consensus. Every single natural language handoff consumes tokens. You're literally paying compute costs for agents to greet each other and summarize meeting minutes.
It's absurd. As the context window fills up with this conversational bloat, the actual core task, writing a mathematically sound function and testing it rigorously, it just gets drowned out by the noise of the simulated environment.
It really does.
I always think about it like hiring a massive committee of 7 highly paid consultants to write a basic Python script. You lock them in a conference room and they spend 90% of the time arguing about the requirements, greeting each other, formatting their inter-office memos, and eating up your entire operational budget.
And meanwhile, the actual coding gets rushed.
Right. And the QA guy sitting in the corner is still missing 20% of the bugs because he's been listening to the programmer rationalize the bad code for the last hour. He's lost his objectivity because he's part of the conversation.
That conversational contamination is the exact failure mode the authors of the AgentCoder architecture zeroed in on.
They saw the bloat and decided to cut it all out.
Exactly. They looked at the landscape and realized that adding more agents, adding more simulated personas does not correlate to better code.
So it does.
True optimization comes from stripping the system down to its absolute bare essentials, defining incredibly strict, non-overlapping roles, and enforcing a strict communication barrier. They wanted to eliminate the conversational bloat to maximize both efficiency and testing objectivity.
So let's pull apart the mechanics of how they actually achieve that. The authors stripped away the product managers, they fired the chatty architects, and they boiled the entire software development loop down to 3 incredibly specific, highly optimized components.
The AgentCoder triad.
Right. The programmer agent, the test designer agent, and the test executor agent. Let's start with the programmer.
Starting with the programmer agent, we're looking at an LLM-powered entity. The underlying engine could be GPT-4, Claude, or an open source model.
Okay, so it's flexible on the back end.
Very flexible.
Yeah.
But the critical difference is the prompting structure. It doesn't just receive a user requirement and immediately spit out a Python script. It is strictly constrained by a 4-step chain of thought process.
So they force it to build an intermediate reasoning space before it writes a single line of actual syntax.
Right. Step 1 is problem understanding and clarification. The model has to explicitly write out its interpretation of the task constraints.
It has to prove it knows what you're asking.
Yes. Step 2 is algorithm and method selection. It has to declare its structural intent, stating whether it will use a dynamic programming approach, a hash map, a nested loop, whatever the optimal path is.
Okay, so it's making a plan.
Then step 3 is pseudocode creation. It drafts the logic in plain English or a high-level abstraction before committing to any specific syntax.
And finally,
Step 4 is the actual code generation.
the inclusion of that pseudocode step seems vital. By forcing the language model to articulate the logic abstractly first, it creates a buffer.
It's a huge buffer. Language models often rush into syntax generation and paint themselves into a corner because they've committed to a specific variable structure early in the output sequence.
Right. They get halfway through a function and realize, oh, wait, I should have used a dictionary here instead of a list, but they've already printed the text.
Exactly. Pseudocode allows the attention mechanism to map the logical flow entirely before dealing with the strict semantics of a specific programming language. It drastically reduces logical dead ends.
Okay, so the programmer is methodically working through its 4-step process. But while that is happening, entirely isolated from that process, we have the second pillar, the test designer agent.
And this is the real paradigm shift.
For anyone listening who builds these systems, this is the part to pay attention to. The test designer is also an LLM, but it operates in a completely parallel, independent universe.
It receives the exact same initial user requirement, but it has zero visibility into what the programmer is doing.
None at all. And it is explicitly prompted to generate 3 specific tiers of tests. Let's talk about those.
The prompt engineering for the test designer is meticulous, and it's adversarial by design. It is instructed to generate first basic test cases.
So just the happy path stuff.
Right. These are designed to verify the fundamental functionality under normal operating conditions. Second, it must generate edge test cases.
This is where it gets tricky.
Yeah, this is where it challenges the code with boundary conditions. Empty arrays, massive negative integers, null inputs, floating point precision limits the exact scenarios that usually cause brittle code to panic.
And the third tier.
Large-scale test cases designed to assess algorithmic complexity and scalability. Ensuring a sorting algorithm doesn't hit a recursion limit or timeout when handed a list of 100,000 elements.
And because it hasn't seen the code the programmer is writing, it can't accidentally write tests that favor the programmer's specific approach.
Exactly. It has to write tests based purely on the theoretical limits of the initial prompt.
But here's where we need to bring these 2 isolated LLMs crashing back into reality, which is the job of the third pillar, the test executor agent.
The grounding layer.
Right. Now, I want to pause here because this is a fascinating design choice. The test executor is not an LLM. It's not a neural network making probabilistic guesses about whether code might run.
No, it's a deterministic Python script interacting with a local, sandboxed terminal environment.
It just grabs the code from the programmer, it grabs the test from the test designer, it runs them together, and it parses the feedback.
The agent loop relies entirely on this deterministic grounding. The user provides the requirement. The programmer generates the code via its chain of thought. Simultaneously, the test designer generates the test suite.
And then the executor steps in.
Right. The executor acts as the sterile laboratory. It runs the generated tests against the generated code. If the code fails, whether it's a syntax error, a memory leak, or a failed assertion, the executor captures the exact terminal output.
The raw stack trace.
Yes. And it feeds it directly back to the programmer agent. The prompt essentially becomes, your code failed on test case number 4. Here is the exact assertion error or type error generated by the interpreter. Fix the code.
And this loop continues iteratively until all tests pass or a maximum iteration budget is hit.
Exactly.
Wait, I'm stuck on a semantic point here that I think is important. We're calling a local Python script an agent.
I know, it sounds a bit counterintuitive.
It feels like a stretch of the definition, honestly. Usually when we discuss agentic AI, we mean an LLM making probabilistic routing choices, utilizing tools, or maintaining a persona. A rigid Python script that just runs a subprocess and returns a stack trace. How is that an agent?
It's a valid semantic debate. In the broader context of multi-agent systems, the definition of an agent has broadened to mean an eponymous node that performs a specific bounded function within a system's workflow. interacting with other nodes.
Okay, so it's a node with agency.
Right. It doesn't strictly require a neural network, so long as it has the agency to execute a task and route the resulting state changes back into the system. It's an executing node.
Fair enough. But furthermore, how does a rigid, traditional script reliably parse the notoriously chaotic text that an LLM spits out?
That's a huge problem in a lot of systems.
Right, because LLMs are conversational. They love to wrap their code in pleasantries like, certainly, I have analyzed the problem and here is the optimized Python code you requested. If you feed that into a Python interpreter, it immediately throws a syntax error.
Oh, instantly. But the methodology here avoids the chaos of natural language entirely through strict formatting constraints. The system prompt for both LLMs explicitly dictates that code must be output within strict markdown boundaries. Code goes inside triple backticks followed by PyCode, and the test suites go inside triple backticks followed by PyTest cases.
So you force the LLM to create a highly specific, regex-friendly container.
Exactly that. The executor script doesn't attempt to process the natural language. It utilizes a regular expression parser to strip away all the conversational filler.
It just ignores the, certainly, here is your code.
Right. It extracts only the payload within those specific markdown blocks. It guarantees an exact, sterile transfer of information. The executor is completely agnostic to the LLM's reasoning or its polite phrasing. It only cares whether the extracted payload compiles and passes the extracted assertions.
That sterile transfer is vital because it cuts out the token bloat we talked about earlier. There is no conversational handoff.
None.
But while the executor provides the grounding reality, the mechanism that actually drives the performance of the thing, that allows AgentCoder to crush the benchmarks, is the blind spot isolation we touched on.
Yes. The separation of the programmer and the designer.
Let's dive deep into the paper's comparison between the single-agent code approach and this isolated triad, because the difference in output is stark.
To understand the mechanism of that blind spot, we have to look at a specific failure mode. The authors illustrate this using a task from the standard HumanEval dataset called has_close_elements.
Okay, what's the premise of that task?
It's straightforward. Write a function that takes a list of floating point numbers and a threshold value, and return true if any two numbers in that list are closer to each other than the given threshold.
It sounds like a really basic math problem. You iterate through the list, you compare every number to every other number, and if the difference is less than the threshold, you flag it.
It seems basic, but let's trace how the single agent system, CodeCode, handles the logic. The single agent generates a nested loop to compare the elements. However, it makes a fundamental classic mathematical error.
What does it do?
It checks if number E minus number J is less than or equal to the threshold. It completely fails to apply the absolute value function, abs.
Oh, wow. Which means if the first number is 10 and the second number is 20, 10 minus 20 is negative 10.
Exactly.
A negative 10 is always going to be less than a positive threshold. So it returns a false positive immediately. It's a logic bug that breaks the entire function.
And this is where the single agent architecture collapses. Because the CodeCOT model generated the code first and then immediately generated the test within the exact same conversational context window, its test generation is poisoned by its own flawed logic.
It's anchored.
Heavily anchored. The attention mechanism of the transformer is highly activated by the syntactic structure it just created. So when it writes the tests, it writes tests that also fail to account for negative differences.
Are you serious? So it writes an assertion that expects the broken code to pass?
Yes. It generates assertions like assert not has close elements, 10, 20, 35.
Which doesn't expose the bug at all. It effectively writes a test designed to pass its broken code, completely ignoring the edge case. It pats itself on the back for a job well done.
It's an empirical demonstration of cognitive anchoring in large language models. If an LLM observes its own flawed implementation, its subsequent verification steps lose all objectivity. It stops testing the theoretical requirements of the prompt and starts testing the reality of its implementation.
But when you swap that out for the AgentCoder triad, the dynamic completely shifts.
Right, because of the isolation.
The test designer agent in this framework never sees the programmer's nested loop. It never sees the missing absolute value function. It is working in a total vacuum, looking only at the prompt. Check if two numbers are closer than a threshold.
So it follows its strict adversarial instructions.
Right. It generates basic tests, edge tests, and large-scale tests based purely on the mathematical definition of distance.
Because it is focused entirely on the problem definition, the test designer generates a highly rigorous, exhaustive suite. It writes tests for empty lists, lists where all elements are identical, and critically, it writes tests checking variations of absolute distances where the smaller number appears first.
It creates a true black box testing methodology.
Exactly.
So when the test executor takes the programmer's flawed code, the code missing the absolute value function, and runs it against the test designer's brutal independent edge cases, the code immediately fails.
As it should.
The executor catches the assertion error, grabs the stack trace, and sends it back to the programmer. And only then does the programmer realize, my logic failed on this specific negative integer comparison. I need to implement the abs function. It corrects it on the next iteration.
It forces the model to confront its own blind spot.
Think about when you write an essay or a really long, complex email. If you proofread it immediately after writing it, your brain literally fills in the missing words because you know what you meant to say.
Oh, absolutely. You just glide right over typos.
You need a second pair of fresh eyes. A copy editor who doesn't know what you meant, who only looks at the raw text on the page. That's what this architecture does for code.
That elegant separation of concerns isn't just theoretical. It translates into hard, undeniable data. When we transition from the theoretical architecture to the experimental results, the empirical advantage of the triad becomes undeniable.
Let's get into those numbers then, because the evaluation wasn't just a small sample size. They ran this across 14 different large language models to ensure the architecture wasn't just overly tuned to one specific engine.
Right, it's a very robust evaluation.
They tested it against 16 different optimization baselines using standard data sets like HumanEval and MBPP. But what's really interesting is they also evaluated it against the enhanced, significantly harder versions of those data sets, HumanEval ET and MBPP2.
For those familiar with the standard benchmarks, the ET variants are brutal.
They really are. They contain much more rigorous adversarial test suites, specifically designed by humans to break generated code that relies on memorized training data rather than true logical synthesis.
So if we isolate the results using GPT-4 as the underlying inference engine for the agents, the performance jump is substantial. Driving the AgentCoder triad, GPT-4 achieved a 96.3% pass rate on the HumanEval dataset and 91.8% on MBPP.
Wow. And just to clarify the strictness of that metric for you listening, we are talking about pass at 1.
Yes, that's crucial to point out.
This isn't, it got the answer right out of 10 different random samples. It means the system, after completing its internal test executor loop, has to provide a final single output to the user, and that final output must be flawless. A 96.3% pass at 1 means it is effectively solving the benchmark perfectly on the first final submission.
The significance of that number becomes apparent when juxtaposed with the previous state-of-the-art framework, MetaGPT, the 5-agent system we discussed earlier.
Right, the chatty one. How did it do?
MetaGPT, utilizing the exact same GPT-4 underlying model, maxed out at a 90.2% pass rate on HumanEval. AgentCoder improved the state-of-the-art by over 6 percentage points.
Which is huge at that level. When you are operating above the 90% threshold on these benchmarks, extracting a 6% gain represents a massive leap in logical robustness.
It's increasingly difficult to squeeze out those upper percentage points. But the accuracy metric is only half the story. The truly disruptive data point lies in the computational efficiency.
The token overhead. This is where the bloated committee metaphors become hard data. The token consumption required for AgentCoder to achieve that 96.3% pass rate was remarkably lean. Only 56.9K tokens processed across the entire HumanEval dataset.
Incredible efficiency.
Compare that to MetaGPT. To achieve its inferior 90.2% score, it burned through a massive 138.2K tokens.
More than double.
And ChatDev, the 7-agent framework, was even worse, eating up 183.7K tokens.
So the triad architecture is delivering superior logical accuracy while consuming less than half the compute resources of its multi-agent competitors.
And the reason for this efficiency maps directly back to the isolated test designer.
Exactly. The researchers quantified the test accuracy, evaluating the quality of the tests generated by the agents themselves. AgentCoder's isolated test designer achieved 89.6% accuracy and 91.7% line coverage on the HumanEval challenges.
It was consistently writing suites that exercised nearly every logical branch of the generated code.
Meanwhile, MetaGPT's QA agent, which is embedded within the conversational bloat of the 5-agent system, only managed roughly 80% coverage.
So to put it bluntly, the 5-agent system is spending twice the compute budget, twice the token cost to hold a simulated committee meeting, and their dedicated QA persona is doing a demonstrably worse job at actually finding the edge cases.
It's practically a satire of corporate bloat translated into machine learning. It really is. But a critical question arises when you look at these numbers. GPT-4 is a massive, highly capable model. Are these massive gains just a byproduct of using a frontier model? What if I'm a developer using an older, cheaper model or a smaller open source model?
Yeah.
Does this triad architecture still hold up, or does it collapse without a massive parameter count?
That's a vital consideration for practical deployment. And the researchers deliberately swapped out the inference engines to test this exact constraint.
What else did they test?
They deployed models like PaLM-Coder and Claude Instant 1 within the triad framework. The performance gains were remarkably consistent. Utilizing AgentCoder improved PaLM-Coder's performance by 32.7% compared to its baseline zero-shot prompting.
32%.
Yeah, it boosted Claude Instant 1 by 42.8%. They even tested an older model like GPT 3.5 Turbo, and the triad architecture pushed its pass rate from a baseline 57.3% all the way up to 79.9%.
That's incredible. So the structural isolation lifts all boats. It empirically proves that the framework itself, the strict separation of generative logic and adversarial testing, grounded by deterministic execution, is fundamentally sound, independent of the raw horsepower of the underlying LLM engine.
It absolutely does.
Which is incredibly promising for developers looking to build local, privacy-focused autonomous systems without relying on massive API budgets.
Definitely.
But whenever a system introduces multiple discrete components, a programmer, a designer, an executor, an iterative loop, the immediate analytical question is, which component is actually doing the heavy lifting?
Right. Did the authors prove that every agent is actually necessary?
Exactly. Are all three pillars of the triad strictly necessary, or is one of them just carrying the other two?
To answer that, we have to look at the ablation studies conducted by the researchers.
Let's break that down for the audience. An ablation study systematically strips away components of a complex system to measure the corresponding drop in performance, isolating the true value of each node.
Right. They focused heavily on the impact of the iterative loop and the individual agent contributions.
Let's tackle the iterative loop first. The system runs the code, catches the error, and feeds it back. Does letting the LLM try multiple times actually result in better code, or does it just spin its wheels and hallucinate different errors?
The data shows a highly predictable and significant improvement curve as the loop iterates. Tracking the pass rates using GPT 3.5 on HumanEval, the pass at one rate on the very first zero-shot iteration was 74.4%.
Okay.
When the executor caught an error and fed the stack trace back for a second iteration, the pass rate increased to 75.6%. By the fifth iteration, it steadily climbed to 79.9%.
Okay, so the feedback loop is empirically effective. The programmer agent is demonstrably capable of ingesting raw terminal errors and successfully modifying its syntactic approach to resolve them.
Yes, the iterative grounding works.
But what about the specific agents? Let's walk through the ablation study where they started unplugging the different personas. They established a baseline by testing just the programmer agent by itself. No test designer, no test executor.
Right, just the language model using the four-step chain of thought prompt to generate code once.
What were the results?
Isolating the programmer agent yielded a pass rate of 61% on the HumanEval dataset. That serves as the baseline measurement of the model's raw generative capability when guided by a structured prompt.
Got it. Then they introduced the first variation. They added the test designer. So now the system has the programmer writing the code and the isolated test designer writing the exhaustive test suite. But, and this is the crucial missing piece, they removed the test executor.
Oh, yes.
They didn't run the code in a Python terminal. They simply took the generated code, took the generated tests, fed them both back into the LLM, and basically asked, hey, based on these tests, do you think this code is correct?
The result of that specific ablation is highly revealing regarding the limitations of language models. The pass rate only saw a marginal increase, moving from 61% to 64%.
Just a 3% bump. Why is it so low?
The reason for this minimal gain is fundamental to how LLMs operate. A test designer generating edge cases without an executor to run them is simply generating theoretical strings of text.
Right, it's writing assert X equals true, but there is no runtime environment evaluating the state of X.
Exactly. The language model is forced to mentally simulate the deterministic execution of the code against the tests. And language models are notoriously bad at acting like a rigid Python interpreter.
They just guess.
They hallucinate the execution results. They assume the code will pass the test because the code looks semantically similar to successful code in their training data.
It's the equivalent of writing a complex physics exam, handing it to a student, but never actually grading it. You just look at the student's confidence level and guess if they passed.
That is exactly what it is.
So realizing that LLMs can't simulate execution, they tried the inverse ablation. They kept the programmer. They brought back the deterministic test executor, the Python sandbox, but they completely removed the test designer.
Right. Instead of an exhaustive suite of edge cases, they just used the 2 or 3 tiny, basic test cases that are typically provided in the standard prompt of the dataset itself.
And how did that fare?
Under that configuration, the pass rate landed at 64.6%.
So it's a slight improvement over the hallucinated execution because the code is actually being subjected to a deterministic reality check.
Yes, but it still drastically underperforms the full system. The bottleneck here is the quality of the tests.
Because it's only using those 2 or 3 basic dataset tests.
Exactly. An executor operating without a test designer is evaluating code against incredibly weak, limited constraints. It's only verifying the absolute most basic functionality. Subtle logical errors and edge case failures easily slip through the cracks, the assertions pass, and the programmer never receives the necessary stack trace feedback to refine the underlying logic.
And then finally, they reconstruct the full triad. You have the generative capacity of the programmer, the exhaustive adversarial edge cases of the isolated test designer, and the cold deterministic reality check of the test executor. All 3 components working in tandem.
And the pass rate instantly jumps to 79.9% for that specific model.
That is a huge leap.
The ablation studies perfectly highlight the necessary synergy of the architecture. You cannot rely on a language model to verify its own logic. You need the creative abstract generation of the code. You need the adversarial independent generation of exhaustive constraints. And crucially, you must have a deterministic local execution environment to prove what actually functions in reality.
Removing any single leg of that stool causes the system's reliability to collapse.
Exactly.
So if you are a listener building autonomous systems, whether that's autonomous coding, complex data pipeline analysis, or interacting with external APIs, the takeaway is absolute. You cannot rely on an LLM to think about whether its actions are successful.
It will confidently, probabilistically hallucinate that it is correct.
Every time. Autonomous systems require grounded execution in a local environment, and they require an independent, isolated mechanism to generate the criteria for success.
The era of simply chaining conversational LLM prompts together, adding more personas to a context window, and hoping that consensus leads to accurate code is ending. The industry is clearly transitioning toward hybrid systems that fuse the probabilistic, creative reasoning of large language models with the rigid, deterministic verification of traditional execution environments.
The AgentCoder framework provides a highly optimized blueprint for that exact transition, which perfectly sets the stage for the final segment of our deep dive. We've unpacked the historical context, the token efficiencies, the blind spot isolation, and the ablation metrics. Now it's time to take these architectural principles and push them to their logical extremes. It is time for novel notions.
I love this segment.
Just a quick reminder for you listening, this segment is for entertainment purposes only. We are pitching outlandish but plausible research ideas inspired by the paper. We take the current data and project it forward.
The triad architecture opens up some fascinating theoretical avenues, particularly when you start playing with the constraints of the personas and the scalability of the token efficiency. What direction are you taking this?
My pitch is grounded in the paper's discovery that independent test designers are vastly superior because they lack the programmer's cognitive bias. But I want to take that independence and weaponize it. I'm calling it the adversarial bounty hunter test designer.
Ooh, bounty hunter. Okay, I'm listening.
Currently, the test designer in this framework is prompted to be thorough. It generates basic, edge, and large-scale tests. But fundamentally, its persona is cooperative. It is part of a system designed to help the overall output succeed. What if we completely alter the system prompt and the reward function of the test designer so its only objective is to completely break the programmer's code? We give it a purely hostile adversarial persona.
So you're taking the concept of cybersecurity red teaming, which is usually applied at the network or application level, and compressing it down to the microfunction level within the agent loop.
Exactly. Instead of just writing standard edge cases like empty lists or negative integers, the bounty hunter agent is given access to historical vulnerability databases, common CVE frameworks, and psychological profiles of common LLM coding hallucinations.
Oh, wow.
Its prompts dictates. The programmer agent is attempting to deploy this function. Your sole objective is to find the buffer overflow, find the memory leak, inject a SQL payload that bypasses the variable sanitization. It gets optimized or rewarded based on the severity of the error it forces the test executor to spit out.
That's brilliant.
We essentially create an evolutionary arms race inside the context window. The programmer isn't just learning to write functional code, it is forced to learn defensive programming through iterative trauma.
The technical plausibility of that is actually quite high, and it addresses a significant limitation in current code generation benchmarks. Current evaluations optimize for functionality. Does the function return the correct Boolean value? But an adversarial test designer would evaluate for security, stability, and resource exhaustion under malicious conditions.
Right. And because the architecture explicitly isolates the test designer, injecting a hostile persona wouldn't conceptually corrupt the programmer's generative process. The programmer is just reacting to the stack trace.
However, the challenge would be bounding the bounty hunter. How do you prevent the adversarial agent from generating mathematically impossible constraints or tests that require external network access just to force a failure? You would need a highly rigid validation layer for the tests themselves.
Right, you'd need the executor to flag if the test itself is structurally invalid rather than the code. But because the token overhead of this triad is so incredibly low, we're talking 56K tokens for an entire dataset, you can actually afford to have this bounty hunter agent spend 10,000 tokens trying to furiously hack a simple 50-line Python script without bankrupting your API budget.
That's a great point.
It flips the economics of security testing. Okay, what is your novel notion?
My concept is anchored entirely in that exact token efficiency metric. The data prove that the three-agent triad requires significantly less compute than the bloated swarms like MetaGPT or ChatDev. Because this discrete triad is so computationally cheap and structurally rigid, you could theoretically nest them. I call the concept fractal agent triads for OS-level development.
Fractal triads. Walk me through the mechanics of that.
Currently, context windows and token costs prevent us from handing an LLM a monolithic prompts like build a new operating system kernel or write a massive enterprise backend. The logical scope is too large and the context window degrades. But what if we introduce a specialized manager agent whose sole function is semantic decomposition?
Semantic decomposition,
Right.
breaking it down.
It takes a massive system-level code-based requirement and logically breaks it down into 500 isolated independent microfunctions. Because the AgentCoder triad is so token efficient, the manager agent can simultaneously spin up 500 independent triads in parallel.
Wait, 500 triads?
Yes. Each individual triad is assigned exactly one microfunction. You now have 500 programmers, 500 test designers, and 500 test executors, all working concurrently in isolated sandboxes.
Oh, wow.
Because the conversational bloat has been eliminated, this massive parallel processing becomes economically viable. You aren't paying for 500 virtual product managers to chat with 500 virtual architects. You're only paying for pure, concentrated logical generation and deterministic testing.
It's pure compute applied directly to the problem. But if you have 500 isolated functions, how does the system reassemble the fractal pieces without everything crashing due to integration errors?
That's where the fractal nature scales up. Once a local test executor verifies that a microfunction passes all adversarial tests, it passes that validated, mathematically sound module up to an integration triad.
Another triad.
Exactly. The integration triad operates one level higher. Its programmer agent writes the glue code to connect the verified modules. Its test designer writes complex integration tests, analyzing the data flow between the modules, and its executor runs the combined build. You take the core victory of this architecture efficiency and logical robustness through strict role separation, and you scale it horizontally.
That is fascinating. It's a method to completely bypass the context window limitations of modern models by treating the triad as a fundamental computational cell.
Exactly.
That is a phenomenal visualization. You're using the triad as the fundamental biological cell of a much larger organism. Instead of trying to build one massive monolithic brain that gets confused by its own context window and bloated by its own internal dialogue, you build a tissue composed of highly efficient, specialized, isolated cells.
Precise.
Both of these concepts, the adversarial bounty hunter and the massively parallel fractal triads, stem directly from the realization that doing more with less is the path forward. Enforcing isolation generates better results than encouraging chatty simulated collaboration.
Synthesizing the broader implications of this entire discussion, the paradigm is clearly shifting. The era of throwing massive, poorly defined conversational swarms of LLM agents at a complex logical problem is demonstrably inefficient.
Also costly.
Highly costly. And the data proves it leads to compromised, biased outputs. The research we've analyzed today proves empirically that achieving true autonomous generation requires a strict separation of concerns. It requires objective, mathematically independent testing, and above all, it requires grounded, local execution to verify the probabilistic generation against deterministic reality.
It is a massive, elegant step forward for the field of autonomous systems. And it leaves me with a final thought for you to mull over as we wrap up today's deep dive. We spent this entire time dissecting artificial intelligence, analyzing how it suffers from a cognitive blind spot, and reviewing the hard data proving that an AI needs an entirely separate, isolated version of itself just to spot its own logical mistakes. But if an artificial neural network suffers that severely from confirmation bias, what does that tell us about our own human cognitive loops? Are you relying on the exact same brain that generated your ideas to test the validity of those ideas?
That's a scary thought.
When you write a project proposal, when you architect a system, or when you formulate a complex argument, are you acting as your own single agent bottleneck? Are you subconsciously generating flawed, easy tests just to make yourself feel right? Maybe it's time we all spun up our own internal test designer personas, a rigid, isolated voice in our head, completely divorced from our ego, whose only job is to brutally test our assumptions against reality.
I think we could all use one of those.
Thank you for joining us for this deep dive on top tensors. Check the bio for the paper link, keep pushing the boundaries of what's possible, and we'll see you next time.